Today we have Arun speaking on From Crystalline Phases of Matter to Bordism.
Thanks very much. It's good to be here. Thanks everyone for being here today. So today what we're going to do is, so this is not well, it's an algebraic topology talk certainly, but there's some physics in here. And even though it is at its core about math. And so what I'm going to do is I'm going to start by telling you about invertible field theories, so a little bit from the physics standpoint of, well, there's a problem that some physicists ask that we can answer conjecturally with this mathematical formalism of invertible field theories. So there's going to be a little bit of physics in there, but the thing is, I learned physics essentially from the school of hard knocks rather than actually from physics classes. So there can't be that much physics in here, and there won't be. But at the same time, if people are interested in hearing more from that side, we can digress and talk about that more. But the point is, I think in the end, there's going to be more math than physics. So the first third, or the first portion, I don't know the fractions of it, is a story that is already sort of well told. It's math research that has been harvested and dried and put into papers about the classification of invertible phases of matter, which is a physics question being turned into a mathematical question, the classification of invertible field theories, and which has largely been solved. I mean, there's still questions, but it's a success story. So then the second third is the newer stuff that is still in progress, and which I will hopefully put on the archive soon. But I think some of you have heard me say this several months ago. So, and this is about incorporating spatial, so symmetries that can act on space in the physics side, and equivariance in the math side, which is always a lot of fun in homotopy theory. So then at the end, and this is a thing which there's some flexibility built in for when it comes to time. I'll talk about, well, you prove these math things, but how do you actually prove them, and how do you actually calculate with them? And that's something that I just find cool, and depending on how hard the problem is, it can be fun. And so that's using the atom spectral sequence, which sounds large, but you do it over something smaller called A1, which makes it tractable enough that I was able to do some things. So I'll do my best to remember to pause for questions every once in a while, but but you are also absolutely welcome to cut me off and ask questions either via chat or however works best for you and for this seminar. So what's the beginning question? Is this study of something called topological phases of matter. So this is a physics thing which does not have a mathematical definition. There are some vague ideas of how it will go, but we don't know how to get there yet, and it's expected to be difficult. So I'll briefly say a little bit about, well, what are these things, but not getting into too much detail, and what we know about studying them mathematically. And even though this is still a big nebulous question, it's still possible to take out some pieces of that question, model them mathematically, and then say, well, this physics thing suggests this mathematical conjecture, which we can prove, and which then gives back to the physics. So that's the kind of mathematical physics, algebraic topology that this talk is situated in. So some time ago, in a university not that far away, condensed matter physicists discovered that there are some materials that they wanted to study. They had this pre-existing Landau-Lifshitz classification of phases of matter, and some things which didn't fit in. So you take some metallic alloy and you cool it to a particular temperature, and then you apply a magnetic field of this particular strength, and then you get this weird behavior. And there's different ways it can manifest, but one which comes up, especially in the stuff that is mathematically formalized by tensor categories, is that these things in these systems, you get things which behave like particles, in that they're, you can sort of tell where they are, or there's a distribution, But then when you compute their statistics, you find that they are not bosons and they are not fermions. And this is weird because all particles are bosons or fermions or things that make them up. So what's the answer? This doesn't break physics. And the answer is that this is interpreted as you have maybe a bunch of electrons and they're entangled in complicated and nuanced ways. And so what this produces is a pattern a pattern which looks a lot like a particle, but it's not actually a particle. But hey, if it helps simplify the analysis to say that this is a particle, then then great. And so that might be how we do it. So in these examples, the particles are the simple objects in some sort of tensor category, but that's not super relevant to this talk. It is cool though. So, okay, we're gonna, what do we do in this kind of science? We find something interesting. Now let's do the Pokemon thing, where we try and fill up the Pokedex and understand what possible topological phases of matter there are out there. And so this turns out to be a very rich and nuanced and hard question. So there's some suggestive evidence, I'll say a little more later, that this classification is related to the classification of fully extended topological field theories. And so what that approximately means is that this is still super open, difficult problem, is saying, well, given a topological phase of matter, how do we mathematically model it? You put it on some medium, which maybe looks like a manifold with triangulation, and then you set up a Hilbert space of states and a Hamiltonian. But there's a lot of details that are important and that we don't know. But it seems possible in some cases to extract a topological field theory out of it, like in the mathematical sense. And classifying topological field theories is also hard. Sure, the cobordism hypothesis is a theorem, thanks to Jacob Lurie, but it's a theorem involving n categories. And so actually explicitly saying, okay, four-dimensional topological phases of matter are classified by this description that's also something we just don't know how to do, even if all the conjectural stuff I mentioned earlier was formalized. And so just digging a little deeper into what are some of these problems. So there's the standard issue, which is that for several decades, we've been stuck on how do you make quantum field theory like things into mathematics. Quantum mechanics we can do. Quantum field theory is just, there's analytic difficulties, there's deep questions, there's a Millennium Prize. And so some of those problems are easier here, but there's still fundamental difficulties. And on top of that, there's additional surprises given to us by the condensed matter world. And so there are these, if you are a condensed matter theorist, you might write down some of these models of systems that look like they really ought to be topological phases, but they have even more bizarre behavior. Non-topological dependence on like the length, the area of your surface or whatever. Particle-like things, which should be particles, but which are trapped and forced to move in certain ways, just weird stuff. And so you could either say, this is a really cool thing, let me study it, or you could say, well, I want to understand which things don't have this bizarre behavior. And that's also something we just don't know how to do. So, the situation seems hopeless. So let's simplify the problem. Before I go on, are there any questions? All right. So what we're going to do is we're going to restrict to invertible things. And so that has both a physics meaning, which is not completely precise, and a mathematical meaning, which is precise. So let's talk about the math meaning first. So topological field theories are, because they are symmetric, the category of TFTs is a category of symmetric monoidal functors. That itself has a symmetric monoidal structure. And so, if you care about fully extended, maybe there's some n category thing going on here, but those details are not going to come into play right here. So the tensor product is pointwise, which is sort of like, this is a categorified, TFTs are sort of categorified functions, and we take we have a ring structure on functions into C. So we just say that the tensor product of two TFTs evaluated on a manifold, on a Bordism, on anything is evaluate, and then tensor. So if you have not heard, if you don't know the definition of TFT, that's okay, because there are multiple mathematical definitions. But the one we're going to use is the standard concept, which can be formalized in a couple different ways, but it's symmetrical modal functors from a Bordism category into complex vector spaces with tensor product. I'm not going to need too much detail about this, so we'll skate onwards. So there's a notion of an invertible object in a general symmetrical modal category, but we're just going to say that invertible means you can tensor with something else and get the unit. And the unit in this symmetrical modal structure is the TFT, which assigns just the complex numbers to every object, to every manifold, and the identity map to every Bordism. So you have invertibility, which you could say, well, it's really supposed to be data, but there's strong uniqueness condition on that data, so it's all right. And so isomorphism classes, this should say, form an abelian group under this tensor product. So you could ask a mathematical question, which is, given some dimension and some tangential structure, oriented, unoriented, spin, however, whatever kind of TFTs you care about, what is this abelian group? And that's an interesting mathematical question. And here is a reason that physicists care about that mathematical question. So given a topological phase of matter, this is some physics thingy. And so however we want to model it mathematically, there ought to be some description of a low energy limit of this theory. Something where you cut off or ignore higher energy modes. And we don't know how to do that mathematically. And even from a physics perspective, this is a little bit confusing. But the belief is that you should get out at the end a topological field theory in the mathematical sense, and that this should provide either an equivalence of classifications or nearly an equivalence of classifications that you can account for. Maybe you need to take deformation classes or something, but that's definitely not the harder part of this. Well, all of this is hard, but that's hard. But that part is less hard. So therefore, there should be a notion. You take the notion of an invertible TFT and you pull it back to high energy, and there should be. And you should get some notion in topological phases. And this is something that the condensed matter physicists came to independently with a different definition, but then came around to this one. And so you could talk about an invertible phase of matter or a short range entangled phase of matter, or, and this is most common in the physics literature, a symmetry protected topological phase of matter. And so the name is a little bit, it's a little bit imprecise in that these were originally thought of as phases of matter where you have some symmetry, and with the symmetry, it's non-trivial, and without the symmetry, it is a trivial theory. But that's not exactly accurate. It's close to the same thing as invertible, but not quite. So the point is there's some notion of invertible phase. There's some notion of tensor product of phases of matter. And so if we want to classify invertible phases of matter, which the physicists were already doing, then we can try and classify invertible field theories, which is a mathematical question. Which is, okay, that's what this says, great. And this is how, this is how, or one perspective on mathematical physics, which is the physicists are trying to do something. How can we first mathematically model it as a concrete mathematical question? And then how can we solve that mathematical question? And finally, what does that tell us about physics? So this was taken up by Dan Fried and Mike Hopkins in a paper that appeared on Archive in 2016, and I think is coming out in the journal this year. It's called Reflection, Positivity, and Invertible Topological Phases. It's a long paper, but there's lots of good stuff in it. So the idea behind this classification is that you can, inside any symmetric monodal category C, there is something called a maximal Picard subgroupoid. So let's dig into this. So you can there's two different notions of invertibility in a symmetric monodal category. Morphisms can be invertible under composition. So if you take only invertible morphisms, you get a monodal groupoid. And objects can be invertible under the tensor prop we discussed a slide or two ago. And that's different. And so if you only take and tensor product convertible objects, you get what the Picard groupoid. Picard because it's modeled on the Picard of a ski. Unfortunately, it's not a Star Trek reference, I think. And so just as you can take the you can take invertible objects in a ring, or invertible elements, whoops. You can take the maximal Picard subgroupoid of a symmetrical nodal category. And so what you're saying is that you, just like invertible functions on a space valued in C, invertible means it factors through C star because you can't divide by 0. We're saying that an invertible TFT valued in vect C, which is this one in this case, is the same data as a TFT that factors through the maximal Picard subgroupoid of vect C, which I'll say a little more about in a sec. So that's on the codomain side. Now let's talk about what's going on the domain side. So you could, if you know, so let's say F is one of these maps. If you know that, well, you know that this is invertible. So you can say, if I have an invertible object in here, f of x inverse is f of x inverse. Sorry, that's not super precise, but it says that for symmetrical nodal functors for a symmetrical nodal functor, if you know its value on an invertible object, you know its value on its inverse. And so what you can do is you can formally add all inverses to this symmetrical nodal category, and that's the sort of Picard groupoid completion. And so if you like algebraic K-theory, there's a good chance you're at the Regensburg conference this morning, but it's, this evening in Germany. But anyways, this is a lot like a K-group. You're adding formal inverses for everything. And you can think of this as some sort of group completion. Well, groupoid completion. So now, okay, we've quote reduced unquote to classifying maps between Picard groupoids. So more homotopy theory helps us here. So let's say that we take, if you have a symmetrical nodal category, then you can take its nerve, which is a simplicial set, and then geometrically realize to a topological space. And the symmetrical nodal structure defines an E-infinity structure on this topological space. So you want to say it's a topological monoid, but there's up to homotopy, the EN operads are exactly the help makes. And okay, so pi 0 of this symmetric monoidal category's geometric realization is the monoid of objects under tensor product. So if all objects are invertible, that's a group, and abelian group even. And so what we have is a group-like E-infinity space. And those are the magic words that allow you to turn this into a connective spectrum. So moreover, there is a Folk theorem called the one-dimensional stable homotopy hypothesis. And I say Folk not because it's not been proven, but because it's been proven by many different people in many different ways. And it says that maps between Picard groupoids are equivalent to maps between these spectra that get spit out. So we have, just to recap, we have a machine which takes Picard groupoids, which we got because we wanted to classify invertible field theories, and you run the machine for a while, and you get out spectra, and you just have to classify maps between these spectra. So if you get good spectra that aren't terrible to work with, this is tractable. I probably should pause here for questions because it's been a little while. So if you have questions, please let me know.
Is there a relation between these invertible field theories and like maps out of the localization of the Bordism category?
What do you mean by localization?
I mean, you take like the groupoidification of the category.
Yes, that's what I was. That's
that
the
is
same thing.
what the Picard groupoid completion is. Okay.
Yes.
Okay, same thing. Okay. Well, oh, I guess. I guess
Same idea.
my thing, you don't add objects. You kind of, I guess it doesn't really involve the monoidal structure, so maybe it's not really what you want to look at.
So this is there's a place where I've seen something like this, and that's Arun Galatius' PCMI lectures last year, where he so the way that he covers this kind of classification among other things, and the way he goes about it is he first says, forget symmetrical nodal structures, we just want to study functors between these things. And so what he calls a poor person's invertible field theory is where you localize, you groupoidify as exactly as you said, and then classify functors there. And then, once that makes sense, then you add symmetrical structures.
Okay.
So so it is, there's good stuff there, even if it's not exactly the same. It's definitely the same idea.
Cool. All right, thanks.
Yeah, thanks for asking. Are there more questions? Okay, I'll continue on, but whenever you have questions, please ask, please ask me. I'm going to keep chat open and I'll keep my ears open, and it'd be good to have questions. So, this conveniently enough, Galatius is the same Galatius. So Søren Galatius, Ib Madsen, Ulrika Tillman, I don't remember Weiss's first name, and I don't remember Nguyen's first name, but they determine this classifying spectrum. And so they say it slightly differently, and that GMTW determined the space, and then Nguyen determines the infinity structure, which recovers the spectrum. But the point is, we know what the domain's classifying spectrum is. So we Picard groupoidify, and this is what we get, and it is called a Madsen-Tillman spectrum, which and what it really is it's a Thom spectrum. And if you're used to the Thom spectra defined in Bordism theory, you start with a vector bundle over BO or BSO or B spin. And what we're doing is we're starting with a vector bundle over BON or BSON or B spin N or something. So that makes it a little harder, but that's fine. That is a thing which we can work with. And then we have to truncate, which is for category number reasons. The codomain is actually a lot easier. So for just complex vector spaces, if we take the Picard groupoid of units, well, let's just do this right now. So you have one isomorphism class of objects, which is the one-dimensional complex vector spaces. And what are the automorphisms of the unit object? Well, it's C star, because it's every invertible maps from C to C. Spectrum, because one homotopy group, it's in degree 1 and it's C star. So it has to be this Eilenberg-McLean. So this is good. This is a spectrum which we can work with, because it could have been something really hard. What if it was TMF? Well, that would have been cool, but it's So you could also you could, if you like superalgebra, which comes up if you care about TFTs with spin structure or fermions in your topological phases, then you need supervector spaces. So in this case, there are two invertible objects, the even line and the odd line, and the tensor product behaves, there's a sign in the symmetry of the symmetric monoidal structure. And the upshot is that you get pi 0 is Z2 and pi 1 is C star, and the K invariant is non-trivial. And so what you get is a variant of the Brown Kamenetz dual of the sphere, which is probably most appropriately called the Punchaugen dual, because maps into it are classified by maps from homotopy groups into C star. So invertible TFTs, at least before we categorify, are classified by cohomology or homotopy, and that's not too scary. And I mean, they're still going on with truncations, but let's sweep it under the rug. I'll briefly say how this should generalize to fully extended TFT, not because I really like infinity and categories per se, but because these are the TFTs that appear in physics. And so this came out of a physics problem. So this is the kind of, we want the approaches that scale in this way. So the homotopy type of the Bordism infinity N category is due to Chris Schomerpriez in a paper from a couple of years ago. And we once again get a Madsen-Tillman spectrum, and it is no longer truncated. So that's nice. Yeah, I like this paper a lot. It's not, so as far as the codomain, well, even before the homotopy type, what category are we using? So Fried-Hopkins, again, used the Punchaugen dual of the sphere, this time a little bit higher up, because just because of where we want partition functions to be. But they do this based on an ansatz from physics. So it would be wonderful if we could see that mathematically. So you write down some n category that is algebraic, and you get out this thing. But that's going to be hard because the homotopy groups of this know the homotopy groups of the spheres. So something interesting is going on there. So if up to category number 2, then this does work. So we had super vector spaces in category number 1, and then above that you can take complex superalgebras, which Dan proved, and then I didn't realize this when Sam and I proved it, but Dan has it in some lecture notes from 2014, and then Sam Gunningham and I studied this a couple years ago. But then after that, it's just this open question. What's up?
I is what, the free infinite loop space, like S infinity?
Sorry, this is interpreted as one object.
What is I?
I is the I don't know if it has a name, but I would call it the Brown-Kamenetz functor. So in general, if you have a I think what you need is either divisible or injective abelian group A. Then you get a spectrum IA, such that maps into it are classified by Homs from pi n into A, and then okay, you need, well, that determines an isomorphism class of spectra.
Yeah. Okay. Sorry, I missed it.
Class. No, don't apologize. Well, I also didn't say any of that. I just said there is this object and the notation, it's, I didn't talk about the notation. So sorry for the confusion.
Yeah, thanks.
Yeah, thanks for asking. So yeah, this is the thing studied by Brown and Kamenetz, but they used Q-mod-C. Before I go on, are there more questions? Okay, please keep asking questions. They've been great so far. Oh, and then we also needed the stable homotopy hypothesis. I know this is a theorem in category number 2 due to, I think, Gursky, Johnson, and Osorno. But then after that, it's still not clear, although presumably true. So there's another thing that we need to fix coming from physics, and I'll say this a little bit briefly. So if someone hands you a quantum field theory, and it comes from physics, which is a vague term, then that quantum field theory had better be unitary. And so there's vague definitions, which, okay, there's a time evolution determined by the Hamiltonian, and it had better act by unitary transformations. And then, okay, some physics things happen that I haven't read the QFT books, so bear with me. But there's a thing called Wick rotation, and the upshot is that if you work with Euclidean field theory, which is what we've secretly been doing the whole time, then you don't get unitarity, you get something called reflection positivity. Well, what is reflection positivity mathematically? Good question. Theo Johnson-Fried has a paper on this. The paper is called Spin Statistics something unitarity, maybe Spin Statistics Orientations Unitarity, and it's a cool paper. But the point is that doing this for TFTs in general, especially extended TFT, this is an open question that people in TFT would be very happy if someone solves. There may be some people working on it, so I don't know for certain, but this is important and confusing. So what Fried-Hopkins do in this paper is that they provide an answer in the invertible case, and reflection positivity gets translated into Borel equivariant homotopy theory. So you have your domain and codomain categories get Z2 actions on them. And you ask your invertible field theories to have equivariance data. And so when you run the infinite loop space machine, you get out spectra with Z2 action. So depending on what kind of homotopy theorist you are, you either say, yay, it's not genuine equivariant homotopy theory, or you say, oh, it's not genuine equivariant homotopy theory. But you pick. But it turns out that if you actually play with this Borel question, then you could, meaning Dan Fried and Mike Hopkins, can reduce this to a simpler non-equivariant question. This is what, so their paper is 130 pages, and part of it is because they do a lot, and this is one of the things they do, which does not take a whole lot of pages. So, so they, there's just some algebraic topology calculations that show that in the end, these things are the same thing as, the maps between these spectra, but without this equivariance needed. So if you care about SPTs, then you take deformation classes instead of isomorphism classes, which just means that you replace IC star with IZ. And now I need to add a caveat to the question that you asked, which is that IZ, so Z is neither divisible nor injective. So what is IZ? Well, it's just convenient notation for the Anderson dual of the sphere spectrum. So, what that is, well, okay, there's different ways of saying it. You could say it's the dualizing sheaf on spec S, but a more down-to-earth way of saying it is that it is, so its generalized cohomology theory satisfies the following universal property. It's a universal coefficient theorem-like thing. We take x of pi n minus 1, so the torsion part of pi n minus 1 non-canonically, and hom of pi n, so the free part of pi n non-canonically, and we put them together. So the only thing, there are only two things in algebraic topology that are not natural with respect to continuous or smooth maps. One of them is Poincare-Gaudy, and the other is the universal coefficient theorem splitting the sequence. And sure enough, this sequence splits, but not naturally. So again, just a reminder, this notation is not what I said earlier about I, but this is related to IC star. So this is hopefully not the worst notation. So, okay, this is a thing where maps into it are things that we can compute in terms of homotopy groups. So that's all right, that's good. And now what's this thing? So I told you Madsen-Toman spectra were unstable in the sense that we use BON instead of BO. And so when you incorporate equivariance, you stabilize, which is this kind of, so this is actually an interesting thing in that you would not have, like that, you've gone down the math rabbit hole from your physics question. And now you get this interesting mathematical fact that, classifying invertible field theories is sort of unstable, but classifying reflection positive ones, no matter what structure you started with, your H-Bordism, no matter how fancy it is, okay, assuming it's reasonable and satisfying a checklist, the stabilization exists and just happens. So these are things like MO for unoriented, MSO for oriented, M-spin for spin theories, but they can be quite a bit more complicated if you want them to be, depending on what kind of physics question you're asking. And so, fortunately, people spent a lot of time from the 40s to the 70s computing a whole bunch of Bordism groups, and that makes my job easier. So thank you, people who did this from the 40s to the 70s. So in examples, this group is what gets computed. So there's the answer. We went through this long, complicated process and got out that answer. Brief aside, that if you take the torsion subgroup, you get the topological theories, and conjecturally, the entire thing classifies all invertible field theories. So these don't need to be topological. Maybe they should depend on a Riemannian metric or like a connection on a vector bundle or something. This is not real math yet, but as Dan Fried puts it, these are not theorems, but they're conjectures, but in the sense that once the definitions are in place, they will be theorems. There's no question about, in his opinion, there's no question about whether they're right or not, just how to make them work. So there's some work on non-topological functorial field theories. So there's some work of Santosh Kandel, there's the Dye-Fried theorem, there's some work of Adrian Clough, although not exactly on this perspective. But this is one of the many pieces of this that is yet to be understood. And yeah, there's a lot of pieces that need to be understood. So are these assumptions valid? So on this cliffhanger, I'd like to pause and ask for questions. Just so please ask away.
Hey, Arun. I was just wondering about what you're saying about the infinity n categories. So like in case
here,
when you're discussing target categories for
yes,
like board 02 or something. And you're talking about this unsats. Like I would think that like it would not be a suspension of like IC star, but maybe it would instead be a wreath product of like in the case of infinity two categories. You're trying to find a part category. Like it would be like the classifying space of that would be like a wreath product of sigma n with the KZ2s. Like just thinking about like when like sometimes people use two vector spaces as a convenient target category.
Right. Well, that'll get you HC star again, sigma 2 HC star.
Yeah, it's like the KZ2s come up like from as like they come from like like the KZ3s come up as like a KZ star 2. Just in the same way that it comes.
Oh, I see. Right. So yeah. Okay.
But like there's also I mean maybe there are different target categories that like are convenient, or maybe they're different, just like they're different notions of what a two vector space is, all of which give convenient target categories. Maybe Fried Hopkins things work, and maybe this thing also works, but I don't know. It just looked a bit weird.
Well, the good news is, so the bad news when things look weird is that they look weird. The good news is when things look weird, that means there's good math to do. So I'll tell you what I know about the two category case.
Yeah.
So there's, you could roughly divide things into super and non-super. You know, this is the Incredibles way of looking on life. And so I'm sure Syndrome has some stuff to say about this, but we're not going to worry about that. So in the ordinary non-super case, then there's two vector spaces. There's the Morita category over C. There's, you know, there's a bunch of different things. And I can't speak to the infinity two case, but I can speak to the two category case. And there's a theorem tucked in an appendix. Shoot, I forget who did this. But they basically they showed that all the different ways of doing two vector spaces, and roughly all targets you would use for two categories that are so two and not infinity two, and regular and not super, and all over the complex numbers are all the same. You get sigma 2 HC star, and if you turn on the topology on C star, you get sigma 3 HZ, as you mentioned.
Yeah, I think it's like there are two like competing models that are used for two vector spaces. So you're saying that
they both give the same answer.
Like what am I giving? I mean, maybe I'll ask you afterwards, but
sure. Let's talk about it more afterwards then, because I don't remember it off the top of my head.
Yeah.
And that way.
Yeah. I'll waste your time after.
Cool.
Okay.
I do not think it will be a waste of time.
All right.
So we'll bookmark that for later. In the meantime, are there more questions about any of this? Okay. Well, again, please keep them coming. These have been great questions. Right. So where were we? We were saying, is this actually good? So how are we going to do this? Well, there was a physics problem. There was physics a long time ago. And what we're going to do is we're going to say, well, the physicists made some computations, and we made some computations, we meaning Dan Fried and Mike Hopkins in their paper, but also some others. So Jonathan Campbell did some. And so we can look at these computations and say, well, do they match? And the more things match, the more likely that we did at least something right. And do they match? Not perfectly, but pretty well. And you can systematically account for the discrepancies. And that suggests that we're on the right track. And then, so after that, not theorem, but proof of concept of the ansatz and the theorems that follow from the ansatz. This approach has been used in physics papers. So you can read physics papers which have some amount of Bordism in them, or spectral sequences, even the atom spectral sequence. And, you know, coming from if you had told me this before I started learning this whole field, that would have absolutely, you know, my head would have exploded. Spectral sequences in physics. So this has been a condensed matter story, but there's also the high energy physics field. And so there, people study anomalies via invertible field theories. And this is a whole nother interesting story, but that's a story for another day. But there are Bordism calculations in those papers too. And things match, the physics matches the math. And this is a good sign that despite the large number of hypotheses we made along the way, that this is correct. So you could try and justify some of these hypotheses, but today what we're going to do is something different. So a lot of the condensed matter physics questions coming out of topological phases also care about spatial symmetry. So you have your Hamiltonian on a lattice or something, and it is invariant under rotations by pi over 2. Yes. And sometimes people care about classifications which know that symmetry and preserve that symmetry. A good example is that, like, your condensed matter stuff, if you are in a lab, is often a crystal and has a crystalline symmetry, a thing that is easy to forget when I wander off into homotopy theory. But people care about that, so let's care about it too. So, okay, I said that. And so these lead to things called crystalline topological phases of matter. And so again, we'd like to consider the invertible ones, because in general, this is going to be even harder than before. Okay, you probably already knew that we're gonna have to think a little harder. Things always get nuanced. So you can't localize a group acting on a space the same way you can localize most things in QFT. You want your fields to be, you want your QFT data to be something that you can sheafify. So like, or it's determined by gluing together local data, a metric, a connection on a vector bundle, a principal G bundle, a gerb, stuff like that. But group actions don't play well with that. So what is the low energy field theory of a crystalline phase? It's not really clear whether it has one, what it looks like. So some of the physics arguments that study this, and I think the big one is due to Ryan Thorngren and Dominic Elsa. So you take your symmetry, you're trying to like massage it into something which is amenable to field theory arguments. So in math, maybe one way to do this, and I'm not going to get into the details of why you might say this, is that these should be geometric local systems of invertible field theories over space with specified G action. So that is a thing which is mathematical. And so you could imagine this in some sort of way. Well, we have a category of invertible field theories, and maybe it's really an infinity category. And then we have an infinity groupoid because we have a topological space, which is maybe something like the homotopy orbits of Arun. And maybe we want to do something like this. And that, okay, I didn't say enough to make it precise, but you could, and that would provide a mathematical model. And that's not what Fried Hopkins do. So disclaimer, we are no longer in their 2016 paper. We're in their 2019 paper called Invertible Phases of Matter with Spatial Symmetry. So again, to repeat, they don't quite do that, but they're guided by similar ideas. And so they get to an ansatz for classifying crystalline phases. So their ansatz, they state it, they show that it works in like 2 examples. And then, but it's not, it turns out there are many examples in physics that their ansatz doesn't quite apply to. And so what you could have is you could have an internal symmetry, like caring about spin instead of SO. And you have a crystalline symmetry, and these mix somehow. So typical physics papers will say things like a reflection squaring to -1 to the F, or something which is kind of weird when you think about it too hard. But the upshot is that you'll get some sort of, that these 2 symmetries fit into an extension rather than just a product. And so this is a little bit weird for equivariance, but that's okay. So here's what we're going to do. And this is work in progress. But we have so what's called the internal symmetry type. So we have maybe spin N or spin C, and it mixes with the crystalline symmetry G. So G is probably a finite group acting on via some representation lambda, although it could be it could just be an affine symmetry. Oh wait, no, sorry. Once we made this assumption, we should probably restrict to point group symmetries. So I'm going to say that they mix via an extension, and that extension could be non-trivial. And I put spin here, but if you care about spin C, then please decorate these with C's. Same here. So I'm not going to tell you exactly how, because that would take a little too much time, but you use this data to build an equivariant local system of spectra over this representation sphere. So this is the 1-point compactification of RD with the G action given by this representation. And so I want the fiber to be M spin. And so, okay, so you can compute the twisted equivariant generalized homology of this thing. So given by this local system. And that is a lot of words that say something that is not as scary, which is first take a homotopy colimit when you write down this local system a certain way, and then you take the homotopy fixed points. And crucially, because everything is Borel homotopy theory, so just spectra with a G action, this is much easier to manipulate, at least for me, than the fully genuine story that you've probably heard some in previous talks here. So, okay, what are some things that physics tells us should be true that we can test? So one of them is specific computations. So in dimension 2, meaning space-time dimension 2, the physicists say reflection squares to -1 f, which means reflection mixes non-trivially with the kernel of the map from spin to SO. And there should be 8 of these phases, and it should be cyclic. So if you are a numerologist and you say, aha, 8, that's real Bott periodicity, you're right, but that's not a theorem yet. That's just this thing that I'd love to understand someday. And it's also related to 2-dimensional pin minus Bordism, if you know that. So spoiling things slightly. But anyways, we'd better get that 8 out of whatever calculation we're doing. And there's a thing called the fermionic crystalline equivalence principle. And what it says is there's two different knobs we can twiddle. One of them is crystalline, or point group in this case, crystalline phases versus just ordinary invertible phases. And another is non-trivial extension versus trivial extension. And it says that the classifications are the same as long as you flip both the knobs. So non-trivial extension, crystalline, should have the same classification as trivial extension, not crystalline, and vice versa. So this is proposed in various forms and suggested in various ways. And then Thorngren, Elsa, Chong Wang, and then another paper from last year, which has 5 authors. So unfortunately, I don't remember all of them, but Jung Chung Gu is on that one. So then they come out and actually state this. So we had this ansatz that I sort of skated over in the last slide for time reasons. But once you have that ansatz, the fermionic crystalline equivalence principle is a mathematical question that you can prove using homotopy theory, or prove or disprove rather. So part of this paper that hopefully will be on the archive real soon now someday is a proof of that theorem. So there's a couple other general principles out there. We're doing more than just computing things physicists already know how to compute. We're saying you can use this method to derive general principles about these phases and then move faster. So, Liu, Shi, and Liu study glide translation symmetries, and they make a conjecture that gives a formula in all symmetry types. Oh, and so since I'm running a little low on time, I'll just, spoiler alert, we get out all of these. And I might say a little bit about why. So first, how does that actually go? First, we got to simplify the classification question. This is a lot of adjectives. So let's reduce quickly to ordinary stable homotopy theory. And so the way that goes is you write down everything. There's probably a more geometric way to do this, but hey, all of these things are homotopy colimits, and so are Thom spectra, according to Ando, Blumberg, Gepner, Hopkins, Rezg, in a series of papers. And so if you stare at your diagram, your homotopy colimits correctly, you realize that it's just one homotopy colimit, which is the Thom spectrum that you were hoping to get out. And it's usually a little fancier than just like MSO. Not that MSO isn't fancy. And so they're like twisted variants of spin or spin C or whatever. But there are not that many Thom spectra. So you can simplify these things further. Take your weird twisted thing and just write it as M spin smash X, where X is a space or spectrum that you understand. And so the example is that M spin C is M spin smash something which looks a lot like CP infinity. It's a stunted complex projective space. So this is a standard thing called a shearing argument. So what you can do to prove the fermionic crystalline equivalence principle, take the Thom spectrum classifying the crystalline phases that you need and shear it into M spin smash X. Take the Thom spectrum classifying the phases with the internal symmetry, but with the other extension. Okay, there might be more than 2 extensions, but there's a way to switch it, and you shear it. And by sheer luck, they agree. Hopefully this shear pun is okay. I feel a little sheepish about it. But great, QED. So one thing which I do want to dwell on is that I've been a little bit cavalier about the distinction between physics and math in this talk. But this is, with my goal of being a mathematician and writing math papers, it's important to keep precise what is a theorem and what isn't. So the fermionic crystalline equivalence principle is not a theorem on its own. Instead, what is true is that if you take the ansatz and you use that to define crystalline phases, then the fermionic crystalline equivalence principle is a theorem. So this says that, so the theorem is that the fermionic crystalline equivalence principle follows from the ansatz. It is still quite hard, probably, we don't know, it's an open question, to define crystalline phases independent of an ansatz. But we have derived a thing which the physicists have been think is true and have been studying in several examples. And that says, hey, the ansatz is probably on the right track, and so are the physicists. So that's hopefully, well, I think that's a good thing. There's things that seem scary and complicated in the first part of the talk are now there's a little more optimism. So you can also check on examples, and there's mostly agreement with the physicists. We'll skip that, although it's cool. So am I already over time, or do I have a couple more minutes?
You have a couple more minutes.
Okay, cool. So what I'm going to do is I'm going to very briefly tell you how to compute some stuff. And this is, if you hate physics, I don't know why you're here, but thank you for being here anyways. But if you hate physics, then this is pure math. Like it's a good thing to know just for homotopy theory reasons, I think. So I'm going to very quickly say, how do you actually make these computations of twisted spin Bordism groups? And this is a cool story. So I want to share it with you today. And I will make sure, I'm going to be conscientious about time, but that also means I'll take questions after. So right after I'm done. So the atom spectral sequence is big and complicated, but for spin Bordism and related things, it's actually much simpler. So Anderson, Brown, Peterson, in seminal work, basically compute the homotopy type of M spin. And what we're going to do is we're going to they prove that the Atiyah-Bott-Shapiro map is 7 connected, meaning that if you only care about things in dimension 7 and below, you can just throw out M spin and use connective K theory. Now, unless you're a string theorist, physicists care about things in dimension 7 and below. Awesome. And now we use something which Stong calculated, which says that the mod 2 cohomology of KO is A tensor over A1 F2. So the change of rings theorem applies to the atom spectral sequence. So if you want to compute the homotopy groups of KO smash X2 completed over using the atom spectral sequence, it just works out over A1. Now, A1 is a finite dimensional algebra, finitely generated. It's much, much nicer than the entire Steed-Mod algebra. So this, you can sort of, this is the kind of thing you can do while sitting in the back of a talk that you've sort of lost track of. It's just determining the C2 page, as opposed to general calculations, which really need a lot more work. So this is tractable. So I don't know if all of you have seen this before. So sorry for going fast, but you can draw A1 module. So I'll just say what this is. So here is A1 as a module over itself. So the dots correspond to summans as a graded F2 module, so the grading goes up. Square 1 is represented by a line going upwards. So square 1 of this thing is that thing. Square 2 is the curly one. So that's square 2 of this. Here's a square 2, here's a square 2, here's a square 2. Great. This is A1. I look forward to seeing this logo on steak sauce sometime in my life, or on the bottle. And then here's another example, which is the cohomology of RP infinity. So this is what goes away if you use reduced. And then there's this kind of cool looking thing. Bob Brunner has some pictures on his website interpreting these things as art. And I have to agree with him. There's this cool, there's some beauty going on here. So here's an example that came from the classification question. If you care about phases equivariant for rotations and rotations, so a dihedral group symmetry, for D2n, n is 2 mod 4. And then, okay, there's a little more data you have to specify, but this is one of them. Great. So you get a bunch of free summands, A1, and then you get this thing which isn't free. And this only goes up to degree 7. And then there may be additional things in degrees 8 and above that I didn't include in this picture. And we're not going to worry about them because physicists really care about the answer to this in dimensions 2, 3, and 4. So computing X, there's a bunch of different ways to do it. The first thing I would suggest is look it up in Agnes and Jonathan's paper. Their paper from 2018, it gives a bunch of examples, and it really teaches you how to do this from the ground up. And I'm so glad this paper exists. Sales pitch over. There's another common trick is a short exact sequence of modules induces a long exact sequence in X, and so you can use that. Not going to worry about the last resort. So here's what the E2 page looks like. The free summands don't contribute much, and then the one other summand contributes this thing. So vertical lines are actioned by something called H0, and diagonal lines are something called action by H1. I'm not going to talk about that right now, but you can read all about it in that paper I mentioned by Agnes and Jonathan, and it's discussed in various other places too. For determining differentials, Margolis has this wonderful theorem that says free summands don't have any. And there's a bunch of other tricks. So the upshot, these are the two that are relevant for phases, but you get this Bordism group. You get a bunch of Z2s. Margolis' theorem splits this extension. H0 tells you these are multiplication by 2 and not split, so you get Z16, and then you're done. Cool. Atom spectral sequence. So I'll conclude with one thing that is less known, but is pretty and I wanted to say. So let's say you care about spin C. I don't know, because it's an example of a symmetry you might want in TFTs. Or maybe because you like complex orientable stuff, who knows? So there's an analog of this, which was proven first by Anderson, Brown, Peterson, and then you can use something that Adams proved, where you use connective KU. So for spin C, you don't get KU, you get KU plus sigma 4 KU, and that's again 7 connected. So it suffices to determine the KU homology of your space X or spectrum. So we get the same deal, except we work over E1 instead of A1. Now, E1 is an exterior algebra generated by square 1 and then the commutator of square 1 and square 2. So the atom spectral sequence simplifies to X over E1. And now here's the fun thing. Well, okay, I like this stuff. You don't have to, but E1 is an exterior algebra. So this whole thing is honest. It's easier than over A1. The differentials, determining X, determining the module structure. So nice. What's unfortunate is that I haven't seen any computation. Well, I've only seen a very few computations with this in the literature. So I think it's cool. I think it's a fun thing to work with, but there's more out there. The truth is out there. So hopefully when I finish this thing, there will be a few more examples in the world. Yep. Okay. So that's the end. Is just here's another twist on this that is really cool. Sorry, I sped really fast through the computations. Thanks again for being here. Are there any questions?
Well, on behalf of everyone, I'd like to thank you for speaking. It seems there are perhaps no further questions, at least for the recording, so I'll go ahead and stop that now.